Deep learning for visual computing overview. Deep learning, especially in the context of visual computing, involves applying neural networks to process and generate data for tasks such as image recognition, classification, and graphics rendering. The course is structured to provide a solid foundation in deep learning techniques and their applications to visual computing challenges. Core concepts and applications. Artificial neural networks (ANNs). Artificial neural networks (ANNs) are computational models inspired by biological neurons. The core components of ANNs are neurons connected by synaptic weights, adjusted during training. The training process uses techniques like backpropagation and gradient descent to minimize the error between predictions and true outputs. Neurons are typically activated using functions such as ReLU, sigmoid, or tan, which introduce nonlinearities, making it possible for networks to model complex relationships. Feed-forward neural networks. Feed-forward networks are the simplest form of neural networks where the data flows in one direction through the layers of the network. These networks are primarily used for basic classification tasks, but form the foundation for more advanced architectures. Convolutional neural networks, CNNs. CNNs are particularly powerful for image processing tasks as they automatically learn spatial hierarchies of features from images. CNNs rely on convolutional layers that slide filters over input images, extracting essential features like edges and textures. Pooling layers reduce the dimensionality of the data, preserving essential information and improving computational efficiency. Key architectures such as AlexNet, VGNet, and ResNet have significantly advanced image classification. ResNet, in particular, addresses the vanishing gradient problem by introducing skip connections, allowing much deeper networks to be trained. Regularization and optimization. To prevent overfitting, regularization techniques like L2 regularization, dropout, and early stopping are used. Dropout works by randomly deactivating neurons during training, which helps the model generalize better by preventing it from relying too heavily on any particular set of neurons. Gradient-based optimization techniques, including stochastic gradient descent (SGD) and ADAM, are crucial for training deep neural networks. These methods adjust the network's weights in a direction that reduces the error or loss. Transfer learning. Transfer learning involves using pre-trained models typically on large data sets like ImageNet and fine-tuning them for new tasks. This approach is particularly beneficial when you have limited data, as it allows the model to leverage previously learned features, significantly reducing training time and improving performance. Advanced models and architectures. Autoencoders. Autoencoders are unsupervised models that compress input data into a lower dimensional latent space and attempt to reconstruct the input. This process makes them useful for tasks like denoising and dimensionality reduction. Variational autoencoders (VAEs) extend autoencoders by introducing a probabilistic framework, which allows them to generate new data similar to the input distribution. Generative adversarial networks (GANs). GANs consist of two networks, a generator and a discriminator, that compete against each other. The generator tries to produce realistic data such as images, while the discriminator evaluates the authenticity of the generated data. This adversarial process leads to highly realistic outputs, making GANs a state-of-the-art tool for image generation. Recurrent neural networks (RNNs). RNNs are well suited for sequence-based data, such as text or video, as they retain information across time steps. However, traditional RNNs face challenges with long sequences due to vanishing gradients. Long short-term memory (LSTM) and gated recurrent units GRU address this by introducing gates that regulate the flow of information, making them more effective for long-term dependencies. Transformers. Originally developed for natural language processing, transformers use self-attention mechanisms to capture dependencies across input data without the need for sequential processing. Vision transformers (VITs) adapt this architecture for visual tasks, demonstrating competitive performance with CNNs in tasks like image classification. Visual computing challenges. Computer vision. I know, In computer vision, the goal is to extract meaningful information from images and videos. However, challenges like object occlusion, intraclass variation, and illumination changes make this task difficult. Deep learning models, especially CNNs, help overcome these challenges by learning robust features that generalize well across variations in the data. Examples of computer vision tasks include image classification, assigning an image to a category, as demonstrated by datasets like MNIST, handwritten digits, and ImageInit. Object detection, identifying and localizing objects within images using models like FasterRCNN. Image segmentation, dividing an image into segments, such as in medical imaging CT or MRI with 3D-UNet. Computer graphics. In computer graphics, the aim is to generate images from abstract scene descriptions. The challenges here often stem from the high computational costs of rendering, as seen in tasks like solving the rendering equation or generating high-resolution images from low-resolution inputs, super resolution. Neural networks are increasingly used to accelerate rendering processes and solve poorly posed problems, such as generating realistic images from textual descriptions or transforming a low-resolution image into a plausible high-resolution version. Applications of deep learning in visual computing. Deep learning has enabled breakthroughs in both computer vision and graphics, including image generation tools like DALL-E and Gauguin 2 can generate images from textual descriptions, opening new possibilities in art and design. Style transfer neural networks can transfer the style of one image to another, creating stylized artwork from photos. Techniques like StyleGAN allow the manipulation of features in images through operations in the latent space. Action recognition models classify actions in videos, as demonstrated in sports action datasets like UCF101. Pose estimation, estimating human poses from images using deep learning, critical for applications in animation and robotics. Mathematical foundations and learning algorithms. Probability theory. Understanding probability theory is fundamental to machine learning. Concepts such as Bayesian inference allow models to make probabilistic predictions, quantify uncertainty, and avoid overfitting by integrating prior knowledge into the learning process. Statistical estimation. Deep learning models are trained to minimize a loss function, such as cross-entropy for classification or mean-squared error MSE for regression. This involves statistical estimators to make predictions as close as possible to the ground truth, optimizing for both bias and variance to achieve good generalization. Practical considerations. Tools like PyTorch and Jupyter Notebooks are essential for building and training deep learning models. PyTorch provides flexibility for constructing neural networks, while Jupyter Notebooks offer an interactive environment to experiment with models, visualize results, and iterate on solutions. In this lecture, we focus on gradient descent methods, which are essential for training models in deep learning by minimizing error functions. Recap of machine learning algorithms and probability theory. Machine learning algorithms aim to improve performance on a given task by learning from experience, which typically comes from training data. Generalization to unseen test data is critical for a model's success, but this process can be hindered by overfitting or underfitting, depending on the model's complexity. Hyperparameters, which control the model's behavior, need to be optimized through a validation process. In probability theory, random variables represent uncertainty, and they follow probability distributions. These distributions help define relationships between multiple variables. Bayes' theorem allows for inverting conditional probabilities, helping us update beliefs with new evidence. Additional concepts such as entropy and Kullback-Leibler KL divergence measure the uncertainty in a distribution and the difference between two distributions, respectively. Error functions in deep learning. Error functions, also called loss functions or objective functions, are minimized during training to improve model performance. A common approach is the maximum likelihood estimator (MLE), where the goal is to find the set of parameters that maximize the likelihood of the model, given the data. In practice, we minimize the negative log likelihood NLL to achieve this. The process of training a machine learning model essentially reduces to finding the parameters that minimize this error function. The error surface of a model, particularly in neural networks, is a complex multidimensional space. Each point on the surface corresponds to a different set of parameter values, and critical points on this surface can be local or global minima, maxima, or saddle points. Global minima represent the best possible set of parameters, but due to the complexity of these surfaces, finding them can be difficult. Gradient descent. Gradient descent is a foundational method for optimizing models by iteratively minimizing the error function. The basic idea is to start with an initial guess for the model parameters and update them gradually, based on the gradient of the error function. The gradient tells us the direction in which the error increases the most, and by moving in the opposite direction, i.e., along the negative gradient, we can reduce the error. The update rule for gradient descent is straightforward. The next set of parameters is obtained by subtracting the product of the learning rate and the gradient of the error function from the current parameters. Here, the learning rate is a crucial factor. It determines the size of each update step. A learning rate that is too small leads to slow progress, while a learning rate that is too large may cause the model to overshoot the minimum and fail to converge. Jacobian and Hessian matrices. For models with multiple parameters, such as neural networks, gradients, and their second-order counterparts, the Hessians are used to optimize the error function. The Jacobian matrix contains the partial derivatives of a vector-valued function, while the Hessian matrix contains second-order partial derivatives, which describe the curvature of the error surface. The curvature information from the Hessian is essential for second-order optimization methods, such as Newton's method, which use both the gradient and the curvature to improve the efficiency of finding optimal parameters. Stochastic gradient descent (SGD). In practical deep learning applications, computing the exact gradient using the entire dataset can be computationally expensive and memory-intensive. To address this, stochastic gradient descent (SGD) is commonly used, which approximates the gradient by using a small, randomly selected subset of the data called a mini-batch in each step. This not only speeds up computations but also allows training on larger datasets that wouldn't fit in memory if processed all at once. Mini-batch gradients introduce some noise compared to exact gradients, but on average they point in the correct direction, allowing SGD to converge to a good solution. A critical aspect of using SGD is adjusting the learning rate during training, as the noise introduced by mini-batches requires smaller steps as training progresses to avoid instability. Momentum in SGD. To accelerate convergence, especially when gradients are noisy or inconsistent, momentum is often used. Momentum helps smooth the optimization process by aggregating the past gradients and applying them in the current update step. This allows the model to remember the previous directions in which the parameters were adjusted, making the optimization more stable and reducing oscillations around the minimum. The update rule for SGD with momentum is as follows. Instead of only using the current gradient to update the parameters, the algorithm also considers the previous step, scaling it by a factor called the momentum coefficient. This allows the model to continue moving in the same direction if the gradient is consistently pointing that way, reducing variance and improving convergence speed. Adaptive learning rates. Finding an optimal learning rate is challenging, because different parameters in the model may require different step sizes for efficient learning. Adaptive learning rate methods adjust the learning rate for each parameter separately throughout training, allowing for more effective optimization. Common adaptive learning algorithms include Adagrad. This algorithm adjusts the learning rate for each parameter by scaling it inversely, with the square root of the cumulative sum of squared gradients for that parameter. This helps parameters that are updated frequently to take smaller steps, while parameters updated less frequently take larger steps. ARMS prop. This method modifies Adagrad by using a moving average of the squared gradients rather than summing them. This prevents the learning rate from decaying too quickly, ensuring that the model can continue learning effectively throughout training. ADAM. A combination of ARMS prop and momentum. ADAM uses both the running average of the gradients and their square, adjusting the learning rate dynamically based on these values. This approach balances speed and accuracy, making ADAM one of the most popular optimization algorithms in deep learning. Challenges with large batch sizes and ill conditioning. One challenge with optimization is selecting the right batch size for mini-batch SGD. Larger batch sizes provide more accurate gradient estimates but require more computational resources, while smaller batch sizes introduce noise, necessitating smaller learning rates. Finding the right balance between batch size, learning rate, and computational efficiency is essential for effective model training. Another challenge is ill conditioning, where the error surface has steep and flat regions, making it difficult for gradient descent to find the optimal solution efficiently. In such cases, momentum or second-order methods can help, as they adjust the steps taken in steep or flat regions more appropriately. Conclusion. N. Gradient descent and its variations, such as SGD with momentum and adaptive learning rate methods, are at the heart of modern deep learning optimization techniques. Understanding how to minimize error functions efficiently is critical for training deep neural networks. Mastery of these methods ensures that models can be trained effectively, even when faced with large datasets and complex error surfaces. By incorporating momentum and adaptive learning rates, we can further improve the stability and speed of the optimization process. Learning algorithms and probability theory are essential components in deep learning for visual computing. In this context, we begin by recapping core concepts such as feed-forward networks, activation functions, and backpropagation. Feed-forward networks are fundamental, where data flows through layers of neurons in one direction, each neuron applying an activation function like ReLU, sigmoid, or tan. These activation functions introduce nonlinearity, enabling the network to model complex relationships. Backpropagation is the algorithm that trains these networks by adjusting the weights of neurons using gradient descent to minimize the error between predictions and actual outputs. Machine learning is a key part of this discussion. Unlike traditional algorithms, machine learning focuses on letting the computer learn from data examples rather than being explicitly programmed. This is particularly useful in visual computing tasks such as classification, regression, and image processing. In supervised learning, the model learns from labeled data to make predictions, whereas unsupervised learning aims to uncover the structure within the data without labels. Machine learning tasks include classification, where the input is assigned to a specific category, and regression, where numerical values are predicted based on input data. Other tasks like density estimation aim to learn a probability distribution from data, while image processing applications might include denoising or filling in missing parts of an image hole filling. Learning algorithms use experience derived from data sets. In supervised learning, each data point has a corresponding target or label, and the model is trained to predict these labels as accurately as possible. The learning process is evaluated through performance measures P, which could be accuracy in classification or log likelihood in probability estimation. These measures help us assess how well the model performs on unseen test data, which is critical for ensuring that the model generalizes well beyond the training set. One of the challenges in training machine learning models is overfitting, where the model performs well on training data but fails on unseen data. Overfitting happens when a model memorizes the training data rather than learning to generalize. Conversely, underfitting occurs when a model is too simple to capture the underlying patterns in the data. To combat these issues, the capacity of the model must be carefully controlled. A model with too low capacity may underfit, while a model with too high capacity risks overfitting. Hyperparameters, which control model behavior such as learning rate and model size, play a crucial role in determining model performance. Hyperparameters are often tuned using a validation set and should not be optimized based on the test set to avoid bias. Techniques like cross-validation help in determining the best hyperparameters by dividing the data into multiple training and validation sets. The data-driven approach to classification emphasizes collecting a dataset, training a model on this dataset, and evaluating its performance on a separate test set. A simple classification algorithm is the nearest neighbor classifier, which predicts the label of a test image by finding the most similar image in the training set. The choice of distance metric, such as L1 Manhattan or L2 Euclidean distance, is an important hyperparameter in this method. Understanding probability theory is essential in machine learning. Many tasks involve estimating probabilities, such as predicting the next word in a text sequence or identifying objects in an image. Random variables and probability distributions describe the likelihood of different outcomes. Discrete random variables are described by probability functions, while continuous random variables use probability density functions. Multivariate probability distributions are used to describe the likelihood of multiple random variables occurring together. Marginalization is the process of summing or integrating over other variables to obtain the probability distribution of a specific variable. Conditional probability, a key concept in probability theory, describes the probability of one event occurring, given that another event has occurred. Bayes' theorem, which underpins much of probabilistic modeling, is used to update our beliefs based on new evidence. Shannon entropy measures the uncertainty in a probability distribution. It is often used to quantify how much information is gained when observing a particular event. Cross-entropy is a related concept that measures the difference between two probability distributions and is commonly used as a loss function in classification tasks. The Kullback-Leibler KL divergence measures the inefficiency of approximating one distribution with another, though it is not a true distance metric since it is asymmetric. Statistical estimators, such as point estimators, are used to estimate parameters of a distribution from data. A common approach is maximum likelihood estimation (MLE), where the model parameters are chosen to maximize the likelihood of the observed data. This method is consistent, meaning it converges to the true parameter value as more data is observed. In regression tasks, loss functions such as mean squared error (MSE) or mean absolute error (MA) are used to measure the error between predicted and actual values. Regularization is an important technique for preventing overfitting. One regularization method is maximum a posteriori map estimation, which incorporates prior knowledge into the learning process using Bayes' theorem. This approach helps guide the model toward more realistic parameter values by adding a prior distribution over the parameters. In neural networks, different loss functions are used depending on the task. For classification, cross-entropy loss is often used, while in regression tasks, MSE or MA is preferred. These loss functions guide the training process by providing feedback on how well the model is performing, allowing the network to adjust its parameters and improve predictions. Finally, the bias-variance trade-off is a critical concept in model selection. Models with high bias are too simple and underfit the data, while models with high variance overfit and fail to generalize. A good model strikes a balance between bias and variance, achieving low error on both the training and test data. This trade-off is an important consideration when designing learning algorithms and choosing model architectures. In conclusion, learning algorithms and probability theory form the backbone of deep learning. By understanding these principles, one can design models that generalize well, avoid overfitting, and make accurate predictions on unseen data. Mastering these concepts is crucial for excelling in visual computing tasks such as image recognition, generation, and classification. Neural networks and backpropagation overview. In this lecture, we dive into neural networks (NNS), their structure, and how they learn through backpropagation. NNs are a type of machine learning model used for a wide range of tasks, particularly in deep learning, and backpropagation is the key algorithm for training these models by adjusting their weights to minimize errors. Feed-forward neural networks. A feed-forward network is a simple type of neural network where information moves in one direction, from input to output, through hidden layers. Each neuron in the network calculates an activation by taking a weighted sum of its inputs, adding a bias, and applying an activation function. This process converts raw input data into outputs, often used for classification or regression tasks. Mathematically, the activation of a single neuron is calculated by summing the products of its input values and their corresponding weights, then adding a bias term. This result is passed through a nonlinear activation function, which determines the neuron's output. When multiple neurons operate on the same inputs, They form a layer, and these layers are stacked to form a neural network. Layer definitions and network structures. A neural network consists of several layers. Input layer takes the raw data as input. Hidden layers. These layers are where the network transforms inputs through multiple neurons to learn internal representations of the data. Output layer produces the final predictions or outputs of the network. Each layer performs the same basic operations, a weighted sum of the inputs, followed by applying an activation function. The deeper the network, i.e., the more hidden layers, the more complex the representations it can learn. However, training deeper networks requires careful tuning to avoid issues like vanishing gradients. Activation functions. Neural networks rely on activation functions to introduce nonlinearity into the model, allowing them to learn complex patterns. Some common activation functions include: sigmoid maps any input to a value between 0 and 1, often used in binary classification tasks. Tan similar to sigmoid but maps inputs to a range of -1 to 1, useful for hidden layers. ReLU rectified linear unit, a popular function that outputs the input if positive, otherwise 0, helping avoid vanishing gradients in deep networks. Leaky ReLU, a variant of ReLU that allows a small, non-zero gradient when the input is negative. Softmax converts logits into probabilities, used in the output layer for multi-class classification tasks. Backpropagation algorithm. Backpropagation is the key algorithm used to train neural networks. It efficiently calculates the gradient of the loss function with respect to the weights of the network, allowing the weights to be updated through gradient descent. The backpropagation process involves two main steps. Forward pass data flows through the network, and activations are computed layer by layer until the output is reached. Backward pass gradients of the error loss are computed with respect to the weights, starting from the output layer and moving back toward the input. This is done using the chain rule from calculus. The chain rule allows us to compute how small changes in the network's weights affect the final loss. Specifically, it multiplies gradients from later layers by gradients from earlier layers, effectively propagating errors backward through the network. The gradients are then used to update the weights in the opposite direction of the gradient, reducing the error. This process is repeated for each batch of data in the training set, iteratively improving the network's performance. Chain rule and gradients. In a neural network, each layer's output depends on the weights and activations of the previous layer. Using the chain rule, we can express how changes in the weights of one layer affect the final output and loss. For a function composed of several layers, the chain rule allows us to compute the gradient of the loss function with respect to any weight in the network by breaking down the computation into smaller, manageable steps. For example, in a network with 2 layers, we first calculate the gradient of the loss with respect to the output of the second layer. Then, we compute the gradient of the second layer's output with respect to the first layer's output, continuing backward through the network until we have gradients for every weight. Gradient descent and learning. Once gradients are computed, they are used to update the network's weights using gradient descent. Gradient descent works by moving the weights in the direction that decreases the error. The size of each step is controlled by the learning rate. Too large a learning rate can cause the model to converge too quickly or overshoot the minimum, while too small a learning rate makes convergence slow. There are several variations of gradient descent. Stochastic gradient descent (SGD) uses a random subset of data, a mini-batch, to calculate the gradient and update weights, rather than using the entire dataset at once. This reduces computational cost and often speeds up convergence. Momentum helps accelerate SGD by moving the weights, not only based on the current gradient but also on the direction of previous updates, preventing the model from getting stuck in local minima. Adaptive learning rates, e.g., Atom adjusts the learning rate for each parameter during training, allowing for more flexible updates depending on how quickly different parts of the model are learning. Jacobian matrices and higher dimensional gradients. In deep networks with multiple inputs and outputs, We use Jacobian matrices to represent the gradients of functions that map vectors to vectors. The Jacobian matrix allows us to efficiently compute the gradients for all outputs with respect to all inputs in the network, which is essential for optimizing large models. When the network contains multiple layers, the Jacobian of each layer can be computed separately and then combined using matrix multiplication. This allows us to apply backpropagation efficiently even in networks with many layers and parameters. Backpropagation example for a single neuron. For a single neuron, backpropagation involves calculating the gradient of the loss function with respect to the neuron's weights and bias. This is done by first computing the gradient of the loss with respect to the neuron's output, then applying the chain rule to compute the gradient with respect to the activation, weights, and bias. For example, given a loss function and the neuron's output, the partial derivative of the loss with respect to each weight is proportional to the product of the neuron's input and the gradient of the loss with respect to the output. Similarly, the gradient with respect to the bias is simply the gradient of the loss with respect to the output. Summary and practical considerations. In summary, neural networks are powerful models that rely on nonlinear activations and backpropagation to learn from data. The backpropagation algorithm, combined with gradient descent, allows the model to iteratively improve by adjusting its weights in the direction that reduces the error. However, training deep networks can be challenging due to issues like vanishing gradients, which occur when gradients become very small in early layers, making it difficult to update the weights effectively. To address this, techniques like ReLU activations and adaptive learning rates have been developed to ensure that gradients remain large enough for effective learning throughout the network. In practice, libraries like PyTorch make implementing backpropagation straightforward, often requiring just a single line of code to compute gradients and update the weights. Regularization in neural networks. This lecture delves into regularization techniques used in neural networks to reduce overfitting and improve generalization. Regularization methods are essential in deep learning due to the large capacity of models, which allows them to fit training data too well, leading to poor performance on unseen data. We will cover gradient clipping, weight initialization, regularization terms and loss functions, and strategies like dropout and data augmentation. Gradient clipping. Now, one of the first topics discussed is gradient clipping, which addresses the issue of exploding gradients. In deep networks, especially recurrent neural networks, gradients can become excessively large in certain regions of the loss function, leading to significant changes in the model's parameters. Gradient clipping helps by setting a threshold for the gradient values, ensuring that no update step is too large. There are two main types of clipping. Norm clipping limits the overall size of the gradient vector to a threshold. Value clipping limits individual elements of the gradient vector to a maximum value. Weight initialization. Next, we explore the impact of weight initialization on training neural networks. If weights are initialized too small, the network may collapse into near linear behavior, reducing its capacity to model complex functions. If weights are too large, activation functions such as the sigmoid function become saturated, causing gradients to vanish and preventing effective learning. A balance must be struck, typically by initializing weights with small random values. The initialization process aims to break symmetry among neurons in the network, ensuring that different neurons learn unique features from the data. Scaling inputs. To improve the efficiency of learning, it is important to scale the input data. Standardizing inputs by ensuring they have a mean of 0 and a standard deviation of 1 helps the network treat all input dimensions equally, preventing biases in how the model learns. This also affects the early layers of the network, allowing for better initialization of weights. Weight initialization and symmetry breaking. During initialization, care must be taken to ensure that the weights are random and that neurons do not start with identical values. If all weights in a layer are initialized to the same value, each neuron will produce the same output, compute the same gradients, and thus update in the same way, effectively behaving like a single neuron. To avoid this, weights are typically drawn from distributions, such as uniform or normal distributions. Parameter initialization and gradient behavior. The behavior of gradients in deep networks depends on the eigenvalues of the weight matrices and the Jacobian of the activation functions. If the eigenvalues are too small, gradients will shrink as they propagate through layers, leading to vanishing gradients. If the eigenvalues are too large, gradients will grow, causing exploding gradients. Thus, the goal of weight initialization is to keep gradients within a manageable range across all layers of the network. Regularization. Regularization is introduced to control the complexity of models and prevent overfitting. Overfitting occurs when a model learns to memorize the training data instead of generalizing to new, unseen data. Regularization techniques modify the learning algorithm to reduce the model's generalization error without significantly increasing the training error. These methods can include adding regularization terms to the loss function, which penalize large weights, setting constraints on the model's parameters to reduce complexity, parameter norm penalties. A common regularization strategy is to add parameter norm penalties to the loss function. This adds a term to the loss function that penalizes the magnitude of the model's weights, encouraging smaller weights and reducing the model's complexity. One popular method is L2 regularization, also known as weight decay, which adds the squared norm of the weights to the loss function. This discourages large weights by pulling them toward zero, unless the data strongly supports larger weights. L2 regularization weight decay. In L2 regularization, the penalty is proportional to the square of the weights, encouraging the model to distribute its learning across many parameters rather than relying on a few large weights. This type of regularization is particularly effective in neural networks, where the weights can become large during training, leading to overfitting. The effect of L2 regularization is to add a fraction of the weights to the gradients during backpropagation, gradually shrinking them over time. Bias-variance trade-off. Regularization is a tool for managing the bias-variance trade-off. A model with too little capacity will underfit the data, leading to high bias, while a model with too much capacity will overfit, leading to high variance. The goal is to find a balance where the model has enough capacity to fit the training data without memorizing it, ensuring good generalization to new data. Data augmentation. Data augmentation is another powerful regularization technique. By artificially increasing the size of the training set, data augmentation prevents overfitting and improves generalization. Common data augmentation methods in image processing include rotating, flipping, scaling, and cropping images. By presenting the network with variations of the same data, it learns more robust features that generalize better to unseen data. Bagging and dropout. Two additional regularization methods are bagging and dropout. In bagging, multiple models are trained on different subsets of the data, and their predictions are averaged to improve generalization. This reduces overfitting by ensuring that the model does not rely too heavily on any particular set of data points. Dropout, on the other hand, is a technique specific to neural networks. During training, dropout randomly sets a fraction of the neurons in the network to zero, forcing the remaining neurons to learn more robust features. This prevents the network from becoming overly reliant on any individual neuron and encourages it to spread the learning across multiple neurons. Introduction to Convolutional Neural Networks (CNNs). Convolutional neural networks (CNNs) are specialized types of neural networks designed to process grid-like data, such as images, by taking advantage of their inherent spatial structure. CNNs are used widely in visual computing tasks like image recognition, segmentation, and object detection due to their ability to capture hierarchical patterns in data. Core concepts: convolution and cross-correlation. At the heart of CNNs is the convolution operation, which is a mathematical operation used to combine two functions, usually an input signal and a kernel or filter. In image processing, the kernel slides across the input image, applying a function to each subset of pixels to extract features. This operation is crucial for detecting local features such as edges, textures, and patterns. A closely related operation, Cross-correlation is more commonly used in CNNs, although it is often referred to as convolution. Cross-correlation measures the similarity between a signal and a shifted version of another signal. The key difference between convolution and cross-correlation is that convolution involves flipping the kernel before applying it, while cross-correlation does not. The mathematical properties of convolution include commutativity, associativity, and distributivity. These properties are essential for efficiently computing and combining multiple convolutions in deep networks. Convolutions are also equivariant to translation, meaning that translating the input results in a corresponding translation of the output. Discrete convolution and cross-correlation. In CNNs, inputs e.g., images and kernels are represented as discrete data. The discrete version of convolution and cross-correlation applies the same principles, but the operations are performed over pixel grids. For 2D images, the kernel slides over the grid, and at each position, the dot product between the kernel and the overlapping image region is computed. The result of a convolution operation is an output feature map, where each pixel corresponds to the activation of the kernel at a specific location in the input image. Convolutional layers. A convolutional layer consists of several kernels that learn to detect different features. Each kernel produces a feature map by convolving with the input data. These feature maps are then passed through a nonlinear activation function, typically ReLU-rectified linear unit, to introduce nonlinearity into the model. This allows the network to capture complex patterns in the data. One of the main advantages of convolutional layers over fully connected layers is weight sharing. In a convolutional layer, the same kernel is applied across different parts of the input, meaning that fewer parameters are required compared to fully connected layers. This makes CNNs computationally efficient and more robust to translations of the input data. Receptive fields and hierarchical feature learning. In CNNs, each neuron or unit in a convolutional layer has a receptive field, which refers to the region of the input that influences the neuron's activation. Early layers in a CNN have small receptive fields, capturing low-level features like edges and textures. As the network deepens, the receptive fields increase, allowing the model to capture more abstract and high-level features like shapes, objects, or even entire scenes. The hierarchical structure of CNNs means that deeper layers can combine features from earlier layers to form increasingly complex representations of the input. Dilation and padding. To increase the receptive field of a kernel without increasing the number of parameters, dilated convolutions can be used. Dilated convolutions introduce gaps between kernel elements, allowing the network to capture larger scale patterns while maintaining computational efficiency. Padding is another technique used in CNNs to control the size of the output feature maps. Without padding, the size of the output decreases with each convolution, since the kernel does not fit perfectly at the borders of the image. By adding zeros around the edges of the input zero padding, we can preserve the input size after convolution, which is important for maintaining spatial information in deeper layers. Stride and pooling. Stride is a parameter that controls the step size of the kernel as it moves across the input. Increasing the stride reduces the spatial dimensions of the output feature map, effectively performing a downsampling operation. This reduces the computational complexity of the model while increasing the receptive field of subsequent layers. Pooling is another downsampling technique used in CNNs. In max pooling, for example, the maximum value from a region of the feature map is selected, reducing the size of the map while retaining the most important information. Pooling introduces a degree of invariance to small translations, rotations, and distortions in the input data, helping the network generalize better to new data. Convolutional layers with multiple channels. In many real-world applications, input data has multiple channels. For instance, color images have 3 channels corresponding to the red, green, and blue RGB color components. In higher layers of CNNs, multiple channels are used to extract different types of features from the input. Each output channel is computed by applying a unique filter across all input channels and summing the results. The kernel in such layers is represented as a 4D tensor, where the dimensions correspond to the number of output channels, the number of input channels, and the height and width of the kernel. Transposed convolutions. While convolutional layers are used to reduce the spatial dimensions of the input, transposed convolutions or deconvolutions are used to increase the size of the output feature map. Transposed convolutions are applied in tasks like image generation, where we need to reconstruct high-resolution images from lower-dimensional latent representations, as seen in generative models like V's variational autoencoders or GAN's generative adversarial networks. Batch normalization. Batch normalization is a technique used to stabilize and speed up the training of deep neural networks. It works by normalizing the inputs to each layer, ensuring that they have a mean of 0 and a standard deviation of 1. This reduces the risk of exploding or vanishing gradients, especially in very deep networks, and allows for the use of higher learning rates. During training, the normalization is done based on the statistics of each mini-batch. During inference, the running averages of the mean and variance are used to ensure consistent behavior. Batch normalization also helps reduce the network's sensitivity to initialization and can act as a form of regularization, reducing the need for other techniques like dropout. LeNet 5, a classic CNN architecture. One of the earliest successful CNN architectures is LeNet 5, developed by Jan LeCun in 1998 for handwritten digit classification on the MNIST dataset. LeNet 5 introduced many of the concepts that are still used in modern CNNs, such as convolutional layers followed by pooling layers and fully connected layers for final classification. Although training LeNet 5 originally took 2 to 3 days in 1998, advances in hardware and optimization algorithms now allow modern CNNs to be trained on the same dataset in under a minute. Summary. CNNs are the backbone of modern deep learning models for image-based tasks. By using convolutional layers, pooling, and other architectural innovations, CNNs can efficiently capture local and global patterns in data, making them ideal for tasks in computer vision. The use of techniques like padding, dilation, and batch normalization further improves their performance and scalability. In this lecture, we dive deeper into convolutional neural network CNNs, specifically their architectures, visualization techniques, and transfer learning. CNNs are the backbone of many modern computer vision systems, and their ability to capture hierarchical patterns in data makes them extremely powerful for tasks like image classification, object detection, and more. CNN architectures. We start with the AlexNet architecture, one of the first deep CNNs to demonstrate significant performance improvements on large-scale image classification tasks. AlexNet consists of 5 convolutional layers followed by 3 fully connected layers. Each layer in the network extracts increasingly complex features from the input image, starting with basic edges and progressing to high-level features such as objects. A notable feature of AlexNet is the use of rectified linear unit ReLU activation functions, which accelerate training by avoiding saturation, unlike the TAN activation function. To prevent overfitting, AlexNet also employs data augmentation techniques such as translations and horizontal reflections, effectively increasing the size of the training dataset. Dropout is used in the fully connected layers to randomly deactivate neurons during training, reducing the risk of overfitting further. The model is trained using stochastic gradient descent SGD with momentum, and the network's weights are initialized from a normal distribution. AlexNet processes images downsampled to a resolution of 224x224 and uses 60 million parameters to classify images into 1,000 categories. Next, we explore VGNI, a very deep CNN that uses small 3x3 convolutional filters throughout the network. VGNI's contribution lies in showing that increasing the depth of the network improves performance. VGNI has up to 19 layers, with each convolutional layer followed by a ReLU activation function and max pooling layers for downsampling. Despite having more parameters than AlexNet, approximately 140 million, VGNI achieves better accuracy by stacking multiple convolutional layers, which increases the receptive field of the network. The use of small filters allows for capturing finer details in the image while maintaining computational efficiency. This architecture showcases the importance of depth and the careful design of layer structures in CNNs. The next significant leap in CNN architectures is ResNet, which introduced the concept of residual connections. ResNet solves the problem of vanishing gradients in deep networks by allowing gradients to flow directly through skip connections, bypassing one or more layers. This innovation enables the training of much deeper networks, e.g., ResNet 50, ResNet 152, without suffering from the degradation problem, where deeper networks perform worse than shallower ones. ResNet models use blocks of layers that include these residual connections, allowing the network to learn identity mappings if necessary. This architecture demonstrates that more layers can improve performance as long as the network can effectively propagate gradients. ResNet's use of fewer parameters compared to VGNet, despite having more layers, highlights the efficiency of the residual learning approach. After covering these architectures, we discuss various visualization techniques for understanding and interpreting CNNs. One such technique is visualizing the activations of different layers. Early layers in the network detect low-level features like edges, while deeper layers capture more complex patterns, such as shapes or entire objects. Nearest neighbor analysis in the feature space of the last layer is another method, where the nearest neighbors of an image in the feature space are identified to explore the learned representations. Occlusion experiments involve covering parts of the input image and observing the changes in the network's output. This helps in identifying which parts of the image are most important for making predictions. Saliency maps provide a way to visualize the regions of the input image that are most relevant to a particular prediction. By computing the gradient of the output with respect to the input, we can highlight the areas that have the greatest impact on the network's decision. This approach is particularly useful for understanding how CNNs make classification decisions. Another popular visualization method is filter visualization, where the filters learned by the network are visualized. In the first layer of a CNN, filters often resemble edge detectors. As we move deeper into the network, the filters become more abstract, detecting textures, patterns, and even entire objects. These filters can be visualized by maximizing the activations of individual neurons in the network using gradient ascent. A creative application of gradient ascent is Deep Dream, which modifies an image by iteratively enhancing the features detected by the network. This process generates surreal, dream-like images that highlight the patterns that the network has learned to recognize. Feature inversion is another visualization technique that attempts to reconstruct the input image from the activations in a particular layer. This gives us insights into what information is retained at different stages of the network. Next, we discuss texture synthesis, which involves generating new textures by optimizing an input image to match the feature activations of a reference texture in a trained CNN. By adjusting the image to produce similar activations at different layers, the network can synthesize visually similar textures. Style transfer extends this concept by combining the content of one image with the style of another. In this technique, the activations representing the content of an image are combined with the activations representing the style, e.g., textures, colors of another image to generate a new image that blends both aspects. This technique has gained popularity through applications like deepart.io, which allows users to create artistic transformations of their photos. We also explore adversarial attacks, where small, imperceptible changes to the input image cause the network to make incorrect predictions. By carefully modifying the input through gradient-based optimization, adversarial examples can be created that fool the network into classifying an image as something entirely different. These attacks reveal vulnerabilities in CNNs and highlight the importance of robustness in neural networks. In the final part of the lecture, we cover transfer learning, which involves taking a pre-trained CNN and fine-tuning it for a new task. Transfer learning leverages the features learned by a network on a large dataset, e.g., ImageNet, and applies them to a smaller dataset for a different but related task. This technique is particularly useful when the new dataset is too small to train a deep network from scratch. There are two main approaches to transfer learning: freezing the early layers of the pre-trained network and only training the final layers, or fine-tuning the entire network by allowing the weights to update during training. Transfer learning has been successfully applied in many domains, including medical imaging and autonomous driving. Pre-trained models are widely available through platforms like PyTorch Hub, OpenMumLab, Hugging Face, and ModelZoo, making it easy for practitioners to implement state-of-the-art models without starting from scratch. These models can be fine-tuned to suit a variety of tasks, providing a solid foundation for transfer learning applications. Autoencoders are specialized types of neural networks designed to learn efficient representations of data, typically for tasks like dimensionality reduction, denoising, and feature learning. They consist of two main parts: an encoder, which maps the input data to a hidden representation, and a decoder, which reconstructs the input data from the hidden representation. The goal is for the autoencoder to learn an internal representation, or code, that captures the most important features of the input, while being able to accurately reconstruct the original input from this compressed representation. Autoencoders can be trained using techniques similar to those used for feed-forward networks, such as stochastic gradient descent, SGD, and backpropagation, with the aim of minimizing the reconstruction error between the input and output. The reconstruction error is typically measured using L1 or L2 loss, which quantifies the difference between the original input and its reconstruction. Autoencoders are often classified based on the relationship between the dimensionality of the hidden representation and the input. In an undercomplete autoencoder, the hidden layer has fewer dimensions than the input, forcing the network to capture only the most salient features of the data. In contrast, an overcomplete autoencoder has a hidden layer with more dimensions than the input, which can lead to learning trivial identity mappings if regularization is not applied. Complete autoencoders have hidden representations with the same dimensionality as the input, but they are often used in conjunction with regularization techniques to prevent trivial solutions. One of the main benefits of autoencoders is their ability to perform dimensionality reduction and data compression. By learning a compact representation of the input, autoencoders can reduce the amount of information needed to describe the data while preserving its essential characteristics. This property makes them useful for tasks like image compression, where the encoder learns a compressed code that can be stored or transmitted efficiently, and the decoder reconstructs the image from this code. Autoencoders also have applications in denoising tasks, where the goal is to reconstruct clean data from noisy inputs. In a denoising autoencoder, the input is deliberately corrupted, and the autoencoder is trained to reconstruct the original, uncorrupted data. This forces the network to learn robust representations that are invariant to noise and other distortions in the input. Autoencoders can be compared to principal component analysis (PCA), a linear method for dimensionality reduction. When the decoder is linear and the loss function is the mean squared error, an undercomplete autoencoder learns to span the same subspace as PCA. However, autoencoders with nonlinear encoders and decoders can learn more powerful, nonlinear representations of the data, making them a generalization of PCA for more complex datasets. Regularization plays an important role in autoencoders, particularly in overcomplete models where the risk of learning trivial identity mappings is high. One form of regularization is the sparsity constraint, which encourages the autoencoder to produce sparse representations by penalizing large activations in the hidden layer. This is done by adding a regularization term to the loss function that penalizes non-sparse representations, leading to more efficient encoding of the input. Sparse autoencoders are commonly used in unsupervised feature learning, where the goal is to learn useful features for downstream tasks like classification. Another form of regularization is denoising, where the input is corrupted with noise, and the autoencoder must learn to reconstruct the original, clean input. This forces the model to learn more meaningful representations of the data by ignoring the noise and focusing on the underlying structure of the input. Deep autoencoders extend the basic autoencoder architecture by adding multiple layers to both the encoder and decoder, allowing the network to learn more abstract and hierarchical representations of the data. This is especially useful in tasks where the data has complex, high-dimensional structure, such as images or text. Deep autoencoders can be trained using layer-wise pre-training, where each layer is trained sequentially before fine-tuning the entire network. In addition to deterministic autoencoders, there are also stochastic autoencoders, where the encoder and decoder functions are treated as probabilistic mappings. This allows the network to model uncertainty in the data and learn a probabilistic distribution over the hidden representations. In particular, variational autoencoders VAEs are a type of stochastic autoencoder that treat the hidden representation as a random variable drawn from a distribution, typically a Gaussian distribution with parameters mean and variance learned by the encoder. The decoder then generates a reconstruction from this distribution. VAEs are trained by maximizing a loss function that consists of two terms, the reconstruction error, and a regularization term that enforces the latent space to follow a prior distribution, typically a standard normal distribution. This regularization term is measured using the Kullback-Leibler KL divergence between the learned distribution and the prior. VAEs are generative models, meaning they can be used to generate new data by sampling from the learned latent space. One challenge with VAEs is that gradients cannot be directly propagated through the stochastic sampling process. To address this, the reparameterization trick is used, which allows gradients to flow through the sampling process by expressing the random variable as a deterministic transformation of a fixed noise variable. This trick enables efficient training of VAEs using gradient-based optimization methods. VAEs have applications in generative modeling, where they can be used to generate new samples from the learned data distribution. By sampling from the latent space and passing the samples through the decoder, the VAE can generate new data that resembles the training data. However, the generated samples from VAEs are often less sharp than those produced by other generative models like GAN's generative adversarial networks, due to the nature of the learned latent space. In summary, autoencoders are a powerful tool for learning efficient representations of data. They can be used for a variety of tasks, including dimensionality reduction, denoising, and generative modeling. Regularization techniques like sparsity constraints and denoising help improve the quality of the learned representations, while extensions like VAEs enable the modeling of probabilistic latent spaces for generative tasks. Autoencoders continue to play a significant role in the development of deep learning models, particularly in unsupervised and self-supervised learning. Deep generative models are a class of machine learning models that are designed to generate new data that resemble a given dataset. They are widely used in tasks such as image synthesis, data augmentation, super-resolution, and other areas in visual computing. The lecture covers different types of generative models, including autoregressive models, generative adversarial networks GANs, flow-based models, and diffusion models. Each of these approaches has unique strengths and limitations, making them suitable for different applications. Autoregressive models treat the generation of an image as a sequential process where each pixel is predicted based on the previously generated pixels. Specifically, for an image, the autoregressive model decomposes the joint probability of the pixels into a product of conditional probabilities, where each pixel depends on the pixels generated before it. The pixel-CNN model is a classic example of an autoregressive model in image generation. It uses convolutional layers that are masked in a way to ensure that each pixel only depends on the previously generated ones, allowing the model to process the image in a sequential manner. Training autoregressive models involves maximizing the likelihood of the observed pixel values by minimizing the negative log likelihood. One limitation of autoregressive models is that they are computationally expensive because each pixel must be generated in sequence, making them slow when generating high-resolution images. However, they are stable during training and provide exact likelihood estimates, which is a valuable property for certain applications. Generative adversarial networks GANs represent a different approach to generative modeling. GANs consist of two neural networks, a generator and a discriminator. The generator creates fake data samples, while the discriminator tries to distinguish between real and fake samples. The generator is trained to produce samples that are indistinguishable from real data, while the discriminator is trained to correctly classify real and generated data. GANs are trained using a minimax game where the generator tries to minimize the discriminator's ability to differentiate between real and fake samples. The loss function typically used in GANs is based on binary cross-entropy. Deep convolutional GANs, DC GANs, are a variant of GANs that use convolutional layers in both the generator and discriminator, making them particularly effective for generating high-quality images. One of the key advantages of GANs is their ability to generate highly realistic images, but they also come with significant challenges. GANs can suffer from mode collapse, where the generator produces a limited variety of outputs, and training instability due to the adversarial nature of the loss function. Despite these issues, GANs have been successfully applied in various areas such as image generation, style transfer, and super resolution. Stylogen, a popular GAN variant, is known for generating photorealistic human faces and has been widely used in creative applications. Flow-based models offer another approach to generative modeling by learning an invertible mapping between the data distribution and a simple distribution like a Gaussian. The key property of flow-based models is that they allow for both exact likelihood estimation and efficient sampling. The probability of a data point in flow-based models is computed using the change of variables formula, which involves the determinant of the Jacobian of the transformation between the simple and complex distributions. RealMVP is a well-known flow-based model that uses a series of invertible transformations to map the input data to a latent space. These transformations are carefully designed to ensure that the Jacobian remains easy to compute. Flow-based models are advantageous because they provide a direct way to compute the likelihood of the data and allow for efficient generation of new samples. However, they tend to require more complex architectures to achieve the same quality of generated images as GANs or diffusion models. Diffusion models are a newer class of generative models that work by gradually adding noise to the data and then learning to reverse the process. The forward process in a diffusion model involves gradually corrupting the data by adding Gaussian noise at each step, while the reverse process involves learning a model that can progressively denoise the data to recover the original sample. The reverse process is typically parameterized by a neural network that predicts the noise added to the data at each step. Denoising diffusion probabilistic models (DDPMs) are a popular example of diffusion models and have been used to generate high-quality images. The key advantage of diffusion models is their ability to generate diverse and high-quality samples, making them competitive with GANs in tasks like image synthesis. However, diffusion models are computationally expensive because they require a large number of steps to generate a single sample. Each of these generative models has its own strengths and weaknesses. Autoregressive models are stable to train and provide exact likelihood estimates, but they are slow at generating data due to their sequential nature. GANs generate high-quality images but can be difficult to train and suffer from mode collapse. Flow-based models allow for exact likelihood estimation and efficient sampling, but their invertibility constraints can limit flexibility and the quality of the generated data. Diffusion models can generate diverse and high-quality images but are computationally expensive because they require multiple iterative steps for each sample. Generative models have numerous applications in visual computing. One of the most important applications is image synthesis, where models like GANs and diffusion models are used to generate new images that are indistinguishable from real images. This is particularly useful in creative industries such as design, art, and video games, where new content needs to be generated efficiently. Another important application is data augmentation, where generative models are used to create additional training data for machine learning models. This is especially valuable in fields like medical imaging, where labeled data is scarce, and generating realistic synthetic data can improve the performance of machine learning models. Generative models are also used in super resolution, where they are trained to generate high-resolution images from low-resolution inputs. This has practical applications in fields like satellite imaging, where high-resolution images are often needed but difficult to obtain. Generative models are also used in image-to-image translation, where the goal is to map an image from one domain to another. For example, GANs have been used to translate images of horses to zebras and vice versa, or to generate images in a particular style, such as transforming a photograph into a painting. This has applications in the arts and entertainment industries, where artists can use machine learning models to explore new creative possibilities. In conclusion, deep generative models have revolutionized many areas of visual computing by enabling machines to generate new, realistic data. Each type of generative model, whether autoregressive models, GANs, flow-based models, or diffusion models, has its own advantages and applications from image synthesis and super resolution to data augmentation and style transfer. While each approach has limitations, ongoing research continues to improve their capabilities and make them more efficient, expanding their use in various domains. In this lecture, we explore transformer networks, a powerful model originally developed for natural language processing (NLP), but now widely applied to visual computing tasks. Transformer networks were introduced in the landmark paper Attention is All You Need by Vaswani et al. 2017 and have since become the foundation for many state-of-the-art models in areas like image classification, generative tasks, and multimodal learning. The primary goal of a transformer is to map input sequences to output sequences, such as in translation tasks. The core architecture of the transformer consists of an encoder-decoder network, where both the encoder and decoder are built using layers of multi-head attention mechanisms and feed-forward neural networks. The input sequences are broken into tokens, which are embeddings created by converting words, or, in the case of images, pixels into a vector representation. Positional encoding is used to retain information about the sequence order, as transformers lack inherent knowledge of token positions. The encoder processes the input sequence by passing it through several layers, each containing a multi-head self-attention mechanism and a feed-forward network. The self-attention mechanism allows each token to attend to every other token in the sequence, making it possible to capture dependencies between distant tokens. This is a significant advantage over traditional sequence models like RNNs, which struggle with long-range dependencies. The encoder's output is passed to the decoder, which similarly consists of multiple layers that include masked self-attention to preserve the autoregressive nature and cross-attention mechanisms, enabling it to generate output tokens one by one. At the heart of the transformer is the multi-head attention mechanism, which uses multiple parallel attention heads to allow the model to focus on different parts of the input sequence. Each attention head computes a scaled dot product attention by first projecting the input into query, key, and value vectors. These vectors are then combined using the dot product, scaled by the dimensionality of the key vectors, and passed through a softmax function to generate the attention scores. The output of each head is concatenated and projected back to the original dimensionality. In addition to self-attention, the transformer uses positional encoding to inject information about the position of each token in the sequence. Since the transformer architecture itself is permutation invariant, positional encoding is necessary to preserve the order of the sequence, which is critical for tasks like translation or image generation. The encoding is typically done by adding a sinusoidal function to the token embeddings, allowing the network to capture both short-range and long-range positional relationships. After covering the basics of transformers, the lecture shifts to their application in visual computing through models like Image GPT, Vision Transformer VIT, SWIN Transformer, and CLIP. These models have pushed the boundaries of what transformers can achieve in fields traditionally dominated by convolutional neural networks (CNNs). Image GPT, based on the GPT-2 architecture, is one of the first models to adapt transformers for image classification tasks. It treats images as sequences of pixels, converting them into tokens similar to how text is tokenized in NLP. The model is trained in an autoregressive manner, predicting each pixel based on the ones that came before it. Although this approach is computationally expensive, it demonstrates the flexibility of transformers in handling different types of data. Vision Transformer VIT, another breakthrough in applying transformers to image recognition, splits an input image into a sequence of smaller patches, which are then linearly embedded and processed by a standard transformer encoder. Unlike CNNs, which rely on convolutions to extract local features, VIT directly processes the entire image as a sequence of patches, allowing it to capture global relationships in the image. VIT has shown that transformers can outperform CNNs when pre-trained on large datasets, such as JFT300M, and then fine-tuned on smaller datasets like ImageNet. SWIN Transformer Shifted Windows Transformer improves on VIT by introducing a hierarchical architecture with shifted windows to handle high-resolution images more efficiently. Instead of processing the entire image at once, SWIN Transformer divides the image into non-overlapping windows and applies multi-head self-attention within each window. By shifting the windows at subsequent layers, the model can capture long-range dependencies while maintaining computational efficiency. This makes SWIN transformers suitable for a wide range of vision tasks, including object detection and segmentation. The lecture also covers contrastive language image pre-training CLIP, a model that combines language and image information to perform zero-shot classification. CLIP is trained on a large data set of image-text pairs, learning to match images with their corresponding text descriptions. Once trained, CLIP can classify images by comparing them to a set of candidate text labels without requiring additional training. This makes CLIP highly versatile for tasks where labeled data is scarce or expensive to obtain. The contrastive training objective ensures that the model learns meaningful associations between images and text, allowing it to generalize to new tasks. CLIP's architecture consists of two encoders, an image encoder and a text encoder, both of which are based on transformer networks. The image encoder can be either a modified ResNet or a vision transformer, while the text encoder is a standard transformer network. During training, the model learns to project images and text into a shared embedding space, where the similarity between image-text pairs is maximized. The final model is capable of understanding complex visual scenes and their textual descriptions, enabling applications in multimodal learning. In addition to these models, the lecture discusses UnClip, which is an extension of CLIP used in DALL-E 2. UnClip generates images from text descriptions by first transforming the text into an image embedding, and then using a generative model, such as a diffusion model or autoregressive model, to produce an image that matches the embedding. This approach highlights the versatility of transformers in creative applications like image generation and manipulation. In summary, transformers have revolutionized not only NLP but also visual computing. By leveraging the power of attention mechanisms, transformers are capable of processing sequences of various data types, including images, text, and even multimodal inputs. Models like VIT and SWIN transformer demonstrate that transformers can outperform traditional CNNs on visual tasks, while models like CLIP showcase their potential in combining visual and textual information. As research in this area continues to evolve, transformers are expected to play an even larger role in the future of AI and machine learning. This lecture covers neural radiance fields (NeRF) and their use in novel view synthesis, which involves generating new views of a 3D scene from a set of input images. NeRF is a method for learning a representation of 3D scenes using deep neural networks, and it has emerged as a highly effective approach for creating realistic scene representations from 2D images. The goal of neural radiance fields is to synthesize new views of a 3D scene by using a neural network to represent the scene's radiance color and density as a function of 3D spatial location and viewing direction. NeRF takes in the 3D coordinates of a point in space, along with the viewing angle, and outputs the RGB color and density of that point. This process allows for realistic rendering of complex scenes, especially when combined with volume rendering techniques. NeRFs work by projecting light rays from the camera through the 3D scene, capturing how light interacts with surfaces at different depths and directions. For each pixel in an image, a light ray is cast through the scene, and the neural network estimates the color and density at various points along the ray. The final pixel color is computed by accumulating the color and density values using an integration process. This integration ensures that occluded parts of the scene, those blocked by other objects, contribute less to the final pixel color, creating realistic images with depth. The planoptic function plays a central role in NeRF by describing all the visual information observable from any point in space and time. The planoptic function depends on several parameters: the viewing direction TE, PH, the wavelength of light L, the time T, and the observer's position Vx, Vi, Vz. NeRF models a simplified version of this function by focusing on the viewing direction and spatial location, allowing the network to capture the scene's appearance from different angles and depths. NeRF uses positional encoding, a technique similar to the one used in transformers, to map continuous input coordinates into a higher dimensional space. This allows the network to learn fine details by encoding the input coordinates as a series of sine and cosine functions with varying frequencies. Positional encoding enables the neural network to model high-frequency variations in color and density, improving the quality of the rendered images. The rendering process in NeRF involves volume rendering, where the radiance and density values are accumulated along each light ray to compute the final pixel color. The transmittance of light along the ray is also considered, which determines how much of the light is absorbed or scattered as it travels through the scene. The result is a photorealistic rendering of the scene, even for complex surfaces like reflective or translucent materials. One of the main challenges of NeRF is that it requires a large number of images from different viewpoints to accurately learn the scene representation. The model can overfit to a specific scene, meaning that it performs well for that scene, but does not generalize to others. Additionally, training NeRF can be computationally intensive due to the need to sample many points along each light ray. To address this, the lecture introduces Instant Neural Graphics Primitives Instant NGP, a more efficient approach for training NeRFs. Instant NGP builds on the idea of NeRF but introduces a more efficient way to encode positional information using multi-resolution hash encodings. Instead of using fixed sine and cosine functions for positional encoding, Instant NGP learns the positional encoding using a multi-resolution grid of hash tables. Each point in the 3D space is mapped to a feature vector stored in a hash table, and the positional encoding is computed by interpolating between the values of nearby grid points. This approach significantly reduces the computational cost of training NeRFs while maintaining high-quality results. In Instant NGP, the scene is divided into multiple resolution levels, with each level corresponding to a different level of detail in the scene. Low-resolution levels capture large-scale features like object shapes, while high-resolution levels capture fine details like textures and edges. By combining information from multiple resolution levels, Instant NGP can represent both coarse and fine details efficiently. The use of hash tables ensures that memory usage remains low, even for high-resolution scenes. The key to Instant NGP's success is its use of hash-based encodings, which allow the network to learn detailed representations of the scene without requiring a large number of parameters. Hash collisions, when two different points in space are mapped to the same hash value, are handled by the network, which learns to ignore redundant or conflicting information. This enables the model to focus on important details while ignoring regions of the scene that do not contribute to the final image, such as empty space. The Instant NGP architecture consists of a multi-layered perceptron MLP that takes as input the encoded positional information and the viewing direction. The MLP then predicts the RGB color and density for each point in space, similar to the original NeRF architecture. However, by using hash-based encodings and a more efficient sampling strategy, Instant NGP can generate high-quality results in a fraction of the time required for traditional NeRFs. Instant NGP achieves significant speedups in both training and rendering times. While traditional NeRFs can take hours or even days to train on a single scene, Instant NGP can achieve high-quality results in just a few seconds or minutes. This makes it feasible to use NeRFs for real-time applications, such as video games or virtual reality, where fast rendering is essential. In terms of results, Instant NGP produces highly detailed and realistic images, even for complex scenes with challenging lighting conditions, such as shiny or reflective surfaces. The model is also capable of capturing subtle details like shadows and reflections, which are difficult to model using traditional methods. In summary, this lecture introduces neural radiance fields NeRF as a powerful method for synthesizing novel views of 3D scenes from input images. NeRF models the radiance and density of the scene using a neural network, allowing for realistic rendering of complex scenes. Instant NGP improves on NeRF by using multi-resolution hash encodings to encode positional information more efficiently, enabling faster training and rendering times while maintaining high-quality results. Both approaches represent significant advances in the field of neural graphics and are poised to play a major role in applications ranging from virtual reality to film production.